Good morning, everyone. I'm Giuseppe. I work at Jive, and I'm the project manager of the Horizon Europe Radio Blocks project. In this talk, I will present the radio Blocks project, but I will start from the past and how we arrived to radio blocks from a scientific and technological point of view. I will talk about the radio astronomy science technology in the next decade, and how we arrived at this roadmap. So this talk will have some, I will try to present the key questions on the scientific area that led to the technical requirements and their solutions. I will show that it's a very dynamic scientific technological landscape that changed from 10 years ago up to now. That sounds good because that's the evolution of science and technology. And then I will present a radio blocks project and how we address this technological requirement. And finally, I will have some notes about possible collaboration and synergy between the radio blocks and Argos. So, Jive is the processor centers and the support centers of the European network. It's a network of 22 telescopes that include 16 major radio astronomy institutes. You have a map over the corner. So the previous science vision for the EDN was developed in 2007, and you have a PDF, the cover of the PDF there. And it was a very different scientific technological landscape. So the VLBI was just starting. There was still an Argos correlator Jive for the EDN. So there was a need of thinking, so what would be the science of the EDN, the technological requirement for the future, and that was this document. But of course, this document needed an update, so that happened thanks to the Horizon 2020 project Jumping Jive that started in 2017. So 10 years after that, the landscape was very different. So the Jumping Jive was a Horizon 2020 NC project. Jumping Jive is an acronym for Joining Up the User for Maximizing the Profile, the Innovation Necessary Globalization of Jive. Luckily, we managed to have a nice acronym. The main goal was to strengthen Jive and advocate its services to enlarge its partnership in preparation for global VLBI in the area of multi-messenger astrophysics. So there were three main areas. One was advocacy and new partnership for Jive and EDN. The second one was development of new capability for the EDN and for VLBI in general. And then towards the future of VLBI, in particular SKA VLBI and VLBI future definition for the next decade. And this is work package 7 that developed not the EDN science vision, but the VLBI science vision. That was coordinated by Cristiano Ventura at the INAF and Giuseppe and Marguerite Chalmers. So this is a nice document. It's not a PDF anymore, but it's a very nice book. It's not as tall as the SKA ones, but it contains the roadmap for the next decade for VLBI in Europe and beyond. It was developed by more than 80 experts covering worldwide distribution and reasonable balance gender representation. And it describes the state of the art in all fields that it's related to VLBI science and what VLBI can help regarding these scientific questions. So it's not a wish list, but there are often questions where VLBI can provide the answers. And these are the nature of that matter, energy. We had a talk yesterday from Felix about using VLBI for this kind of measurements. And then observing supermassive black holes in the universe, formation of the jet, and the gravitational wave astrophysics, like with pinpointing the very high precision the position of the counterparts of the outflow, wave outflow from this phenomena. Transit universe, like the organization of past radio bars, the morphology of midway, the star formation with the Mesa VLBI, and also the set applications. And at the end, there is a chapter about the physical technological developments to address this kind of science. So now we go from the VLBI. So how can we implement this? So we want to go from the science vision to the technological requirement and development implementation of these requirements. So in particular, these requirements are the development of broadband antennas and receiver systems, high recording bit rates to have a sensitivities, next generation correlator to deal with higher data streams and be more performant, more telescope and a wider frequency coverage, and a wider field of view. So we went then from the VN to the VLBI, and now radio astronomy in general, because these technological requirements are not just related to VLBI, but they are much wider for all the radio astronomy from LOFAR up to And to answer to this question, we proposed the Radio Blocks project that was approved by the DC, and now it started in March last year. So this is a synergy between all the astronomical facilities, VLD network, SKDAs, the VHT, GADA, LOFAR, ALMA, and more. And there is an alignment with the Argos technology. So let's see now radio blocks. So what does it mean radio blocks? First of all, the official name of the project is New Science in Radio Astronomy, applying cutting-edge technology to enhance the entire data chain from receiver to final output. So the acronym was not very good, so we went for radio blocks. And radio blocks because we want to build common building blocks for technological solution that can be applied not just to a single facility, but across facility, across the frequency, across the multiple technological needs. So we want to go beyond the state of art. It's not just using what is now, but to develop new tools for the future. It's work across the whole data chain and enabling a broad range of new science and enhancing the European scientific so the result will be these blocks of technology that can be implemented in multiple facilities. And it's will address questions about digital receiver, data transport, correlator, correlations, detector, data processing. Here you have the main the key points that were in the proposal that I think they were very helpful to convince the EC that this is a very useful project for radio astronomy in Europe. So it's we want to build necessary enhancement in sensitivity and in the field of view in world-class radio facilities, which is I mentioned before, and we want to address the common technological challenges of these radio facilities. From allowing their science, so that's the main goal. We want to produce excellent science. So the proposal was accepted. This is from the EC portal. That's the project name and the acronym Radio Blocks. And it started the 1st of March 2023, and it will last for 48 months. We got about 10 million euros from the EC, and we have many associated partners that are paying more than 3 million euros. We have 23 beneficiaries that will get money from the EC grant, and 8 associated partners. In total, 31 partners for 12 countries, including 2 intergovernmental organizations, ISO and SKDA organizations. The total effort is 1,187 person months, which is quite big. And it's divided in just 5 work packages. Each of these 4 packages, maybe except for the first one, which is project management, they are big projects divided in subtasks. Here you have a table with the work packages, their effort, and all the deliverables. Mostly will happen at the end of the project of month 48, because there will be demonstrators, prototypes that we use telescopes. The governance of the project, so you have the radioastronomical facility and industries that are feeding to the coordinator, and which also is in contact with the C. We have the General Assembly, which is the board of the directors that talk with the coordinators. So then we have a smaller executive teams, which comprise the work package leaders. We have a management team and the work packages. It's very straightforward. A bit more complicated, it's how these things communicate with each other, but that's probably the strength of the project, because all these work package, they are not independent, but they follow the data chain of the radioastronomical observations. And the end results are these building blocks prototypes. So we have the science enabler, which are the field of use, SSD, the bandwidths, that's what we want to achieve. These are the facilities, and the building blocks are on the bottom, and they are all connected to the different facilities. Yeah, a bit complicated, and this is probably even not complicated, but because I will go through this during the talk, it will show the signal chain from when you receive the signal from the sky up to the final data products. And this is divided by work packages. And the arrows is the communication between the different products of the project. So the work package 2 is about the vectors. It's about developing key components for a sensitive wideband receiver for infrastructure like VDN, ALMA, NOEMA, IRM, and the XAA. It's about improving the performance of the individual components along the analog part of the receiver's signal chain. You have a plot, a picture there, and this is the receiver, and you have the signal from the sky, the optics, the LNAs, and the digitalizer. So this work package will work on the optical elements, on the detectors, and the low noise amplifiers, and the local oscillators. The goal is to improve the bandwidth, the sensitivity, the power consumption, the compactness, and the interoperability of these instruments, taking care of RFI. RFI is very important in all parts of the signal chain, from the analog part, the digital part, up to the data processing part. In practice, what they are building are, or try to simulate in some cases, or propose a design. It's radio frequency windows, lenses, and filters for high frequency systems, or meters array. The design of new designs for the horns, zero frequency, SIS mixers that are very important for high frequency arrays, and then RF LNAs, but also IF LNAs, and then the local oscillators. These are the main products of this work package. It's a work in progress, like all the rest that you're hearing today from me, because the project just started, and more will follow. But if you're interested in collaborations or more details, you can contact the work package leaders. I probably should mention here the work package leader are in slides. I didn't put them later because of the slides will be online. Email address, but please contact me if you want to get in touch with any of these people. So we are in this part of the signal data chain. We are the analog part. So we have the optical elements, the mixers, the amplifiers, the oscillators, and then there is a task about a value banded down converter to have like a simultaneous conversion of the whole data times. And this will produce these analog building blocks that will fit then into the digital receivers and then yes, and you go down is the chain. About the receivers, it's about improving the technology in some key areas like the system temperature, but in particular the bandwidth and the field speed. Here now we are from the this part of the project, and it creates a link between the analog part and the digital domains. So at the end, there will be some toolbox that will be practical, that will be used by the facilities, and that will allow the European astronomers to adopt this kind of technological solution for a wide range of instruments, from small and large single dish telescopes up to arrays of different kinds of dish systems like machines or machines. So at the end, there will be developments of prototypes and demonstrators, and they will have different implementation of the visualization. Again, it's a work in progress, and this work package will provide these building blocks for wide field astronomy by implementing new beamforming technology, in particular using this radio frequency system on a chip, RF-SOC, that combines the analog to digital conversion and FPGA instead of chip, so it will be customizable and programmable. Then you have the phase array feeds and the signs and implementations, and the mitigation, RF mitigations already happening in the feeds level. So this will allow like real-time identifications of RFIs and try to remove this stage of the signal chains. Again, this will use a demonstrator that will be mounted at the end of the project. For the wideband astronomy, there will be the development of the DDDC4. It's a VLBI backend. There will be a demonstrator that will be later available commercially after the prototype. And this will allow higher higher bandwidth and higher data rates, and again, also this stage in the recording phase, it will allow the RFI identifications. The RFI mitigation can will happen as well with some studies to use AI to identify the RFIs. And of course, the development of probe and digitizer. And to go to higher frequency, different ways to have multiple things or it's having like multi-pixel feeds state of phase arrays. And it will be a development also in this space. Again, work in progress. We just started. We are in the phase of, but there are many partners involved, interested in this field, including the industry partners. Again, please get in touch. We are in this part of the signal chain. There are different tasks. We see we operate 3.11, 3.12. So this is about the phase arrays. And then at the end, we a demonstrator of the phase array, and then we go down with the phase arrays are mostly for the wide field astronomy, and then we have the wide band astronomy with the program digitizer that you can see, and then with the digitizer building blocks that are both from the receiving system DDDC, and then we will have at the end the DDDC4 prototype. And then for the wide field of web and astronomy, together with the study for the focal phase array. Work package 4 is about correlation. It's about delivering building blocks using commercially available hardware to have the next generation correlators. And this will be used for a wide range of facilities. So there will be not a single correlator, but again, building blocks to allow the creation of the next generation correlators. And that will use new technologies and the exploring technology like GPUs and tensor core, or the so-called DPUs, which are data processing units to do the processing in big data centers. FPGA, of course, and then increasing the input output for data transfer between to the correlator. Again, that will be building these blocks for the next generation correlators. It will be prototypes for ADN, LOFAR, Merging, and ALMA. Work in progress. Please contact. There was recently a meeting of this work package that defined landscape, and it will be a report about that can be found on our website. We are in this part of the data chain, signal chain, data transport and correlations. We want a very high-speed data transfer, and we want effective and performance in the correlation. And now we go to how to process this data. So we need to have a modular, open source, and flexible analysis toolkits to analyze your data that will come from the signals chain. In these slides, you can that will be available. You can read more of the details. You can find all the details in our website. But the important part, the key part, is use the task libraries, which are Python libraries for the open source libraries for developing parallel computing with Python. So they're very useful in this case because you can develop some generic program that are scalable, and that will be the case of 350. So there will be an implementation in the task framework. So the idea is that you can use your own laptop, or you can run the code in a big data cluster using the same kind of library, any big changes. And coming from the ESG imaging, you have different ways of producing imaging from your sparse data, and there will be some studies how to implement that. And the last point is creating a toolkit for phase arrays and so this will be direct for connections with the package suite. We are now at the end. We have the post-processing. So we start to the signal we see from the sky, which is the analog part, and we digitize it, and then correct the data, and we are in the post-processing. And at the end, you will have some data processing building blocks. So, who are the stakeholders? Why we are doing this? For whom we are doing this? So we are doing that for the users of the infrastructure, so they can develop the tools, the radio facilities to enforce the capability, the science and the engineers to improve their know-how. We want to have collaboration with the industry, with other facilities, and of course the policymakers, because we want to facilitate innovations benefits of radio astronomy. We will disseminate these results with publications, with software, with the release and open source and open license. We probably have another community that will collect all these documentations and few months, we got some deliverables, everything checked green. You get the kickoff meeting, and you see the RadioBlocks website. It's very simple at the moment because there are no results, but in the future we'll be updated with all the results, with news, events, and so on. RadioBlocks and Argos, what could be the contact points and the synergies. Of course, in the tier system, in the RF system, and in the DNA, even if they work in area blocks for the DNA, it's mostly at a higher frequency, everything is scalable. So there will be some synergy there. The digital backends, of course, for VLBI, or the serialization, and wide field of view and wideband tools for building blocks. And again, the correlations and the data transport and the tools that we produce for the data reduction and expressions. And of course, once you have your telescope prototypes or full system deployed, there could be some observation with the AM, so there would be an extension of the network conditions. And the results there are because if we start the collaboration, we will be more things that we could discuss. So this is my last slides. You have all the partners, QR code that takes you to the website, and some final thought about the ambition and the impact that the project has. I have stopped here.
So thank you very much. Are there any questions from the people here in the room?
Will there also be a community workshop like this one for RadioBlocks
sometime soon? I don't know, but there will be. We want to organize all the meetings of the project, inviting stakeholders external to the project. Everything is open. Our deliverables are public. So yes, we want to organize a meeting where external partners can answer.
A more technical question. So in your architecture, you are considering that you have the system that receives the signals, and then you transfer the analog signal to a further away point where all the digitization happens, and then it goes for computing and anything else. We have thought of digitizing the signal directly on the field, which is a slightly different approach. We don't have the losses of the analog transfer. Is this something that you consider adding in the architecture as an alternative? Let's say, let's keep off the first part, or the minimization, let's say, of the analog.
Yeah, I think that it's also there between the analog and you can have. I think it depends on the facility. Again, the details that go back to the details will not matter. We won't use the person in charge of them, but it depends on the facility. You have facilities that need the digitalization happening on site because of the data quantity that you want to transfer, and others they don't have that problem, so they can transfer the data to a facility. We have also like single dish, or that's maybe it's different than a distributed array. So, but both options are
okay, so there are two hands raised online. So Jason, please go ahead.
Yeah, thanks for the nice talk and summary of RadioBlocks, Giuseppe. You alluded, I'm assuming, by the way, that you can hear me okay. Is that correct? Or?
Yes.
Yeah, okay. So you alluded to this a little bit in the context of Argos specifically, but I mean, what is the general strategy? Like, what actions are you going to take to ensure that all of this good work finds, operational applications in existing and future telescopes, right? Because there's, of course, always, the danger that there's lots of insights and there's some demonstrations, but it doesn't really, manifest into something that's being used for cutting edge science. What kind of strategies are you going to take there?
There is, well, always the risk, also with the technology that you develop something and then there is something more efficient that they start to appear in the scene. The idea of having demonstrators that will be tried at the facilities, it's a way to mitigate this risk because you have a product which is not just on the paper, but it's like a prototype that is can be tested. And then it's again the core of the project is not the final prototype itself, but the designs of the building blocks. So the building blocks can then be if at the end you have a new facility coming up, can be tuned for this new facility. But I agree with you that it's something that needs to be strategized in case we encounter this risk. The problem also is that most of the deliverables will be at the end of the project. Right at the end. So if something happens there, and we don't see that risk, but it could be that at month 48 we have everything there, and then after the project, everything is stays like an exercise. But we want to push that, and I think that will come from the community. The community is really keen on developing these things. The facility needs these building blocks. So it's not just the project itself, which is a separate entity, but the project is just a sort of coordination of the needs of the facility. So that's why I don't think that we had the problem that there will be no push in that direction.
Okay, thank you very much.
Okay, so Yuan,
Yeah. So just I guess a little bit to Jason's question, but also just a bit of context for some of the relationships that Argos already has with radio blocks. The backend system that we will be developing for Argos is based on this EDD system that we have for Effelsberg, which is the kind of foundational block for what we are turning into the PATH backend processor modular toolkit, which is work package 5.5, which I am the lead of in radio blocks. So my department here is leading work package 3, and we're also building the backend for the PATH demonstrator that will go on to Effelsberg. In fact, we've just bought the cluster for that, which will be installed in Effelsberg before the end of the year this year. So there's already a kind of strong connection here between Argos and radio blocks, where we are expected to use a lot of the same software and hardware, or at least designs. I think that to get to Jason's question about community adoption, this is a difficult point. You're absolutely correct that anyone can go out and can publish their own thing, and there are many different forms of such backends and toolkits around that don't necessarily have community adoption. And I think what Radio Blocks pushes for is very clear documentation and structure for how those deliverables are produced and presented, which I hope makes it easier for future telescopes or future designers of telescopes to consider these frameworks, these packages, these toolkits, and understand easily how to adapt them to their own needs. So when we say PATHs here, we're not just talking about phased array feeds on telescopes, but we're also talking about interferometers as well.
Thanks, Yuan.
thanks, Yuan. So I also have a question regarding the RFI mitigation plans for radio blocks. I mean, is there any plan to investigate things, doing some of that on the RFSO boards themselves? Or what's the
Yes, there is a, okay, here, I think that there is some work that will be done to I think there will be some studies and some simulations to optimize these windows very front end for RF applications. There is some work to be done.
and who is leading that work?
It's Caster Kramer from
Fantastic.
So Caster Kramer, Google's Ilkin 453, John Romain 454, and Robert 455. And just
Excellent. Okay, thank you very much.